In this video I'll be explaining a few equations that which DEMAPS uses to calculate the load and what exactly is exponential moving average uh, which is used in DEMAPS. So first I'll talk about exponential moving average, which is used to calculate the load increase and load decrease tendency. That's the important point in DEMAPS. So before talking about exponential moving average, let's see what is average. If I have three numbers 1, 3, 5, then the average of them is 1 plus 3 plus 5 by 3. So if I have 1 million numbers, then it will be like 1 plus 3 plus 5 plus etc. by 1 million. So, and what is moving average? Moving average is nothing but if I have 1, 3, 5, 6 and the numbers get added every second or over time, if the numbers get added, then if I say I want average of 5 numbers at every time, so it's like 1, 3, 5, 10, 15, 18, 20, etc. and every time I want 5 numbers, then assume that I had these numbers, so it will take this average 1, 2, 3 plus 5, and then the window will keep moving this side. So at a time only 5 numbers are selected to take the average. It's this 5 numbers, then the window will keep moving. So that's moving average. It's not like all the numbers are selected, only 5 numbers are selected in the window and they keep on moving. And what is exponential moving average? Exponential moving average. Exponential moving average is moving average, but the window that's moving over these 5 numbers every time, in that there is a weight given. That's like the new values, these will be the new values over time, and this will be the old values in the window. So the new values will be given more importance by giving them a higher weight. It's like new values are given 0.8 as the weight. It's like if I have a 10 here, it will be multiplied into 0.8 plus if I have a 10 here, then it will be multiplied into 0.2. So 0.8 plus 0.2 is equal to 1. So it's basically something like that. So 0.2 into 10. So it's like 2 plus 8 will be 2 plus 8 divided by 2. So that's 5 is the average. So just these weights are given 0.8 and 0.2. So for the these weights are given such that the new values have more importance. So that's exponential moving average. Now let's see how it is used to calculate the load increase and load decrease tendency. We have seen that we had two words, that is expected load and actual load. These are of each map: the expected actual load of the map, mobility anchor point, and the expected load and actual load of the map. Consider that I had a map, mobility anchor point, which has 1, 2, 3, 4 downlinks, and in one of the downlinks there is one more map, and it has 1, 3 downlinks, and then there is the access router. So the map that is on the top has two works, or it has to allocate bandwidth for two reasons. One is for those mobile nodes that are registered to this map, and the second is to forward the data that is coming from the internet, that is for these maps, that the maps that are under it. So it's like the maps that are below in the hierarchy needs the data to be to the data should reach these maps that are below in the hierarchy, and these data should pass through the maps that are higher in the hierarchy. So this map has two goals. One is to forward the data to lower maps, and second one oh, is to compute and manage the mobile nodes that are registered under that map, registered under that map. So it has two goals, and the bandwidth should be allocated properly to for this job and this job. So that is how it the data transfer works from internet to each of the map to the access router. If I say this as the ith map, then I write the equation for actual load as m of ith map, and this is like 1 2 3, and maybe this each downlink I term it as k, like k is equal to 1 here, k is equal to 2 here, k is equal to 3, k is equal to 4. So each of the downlink is k. So actual load of ith map in its kth downlink at time n, this is the actual load, is equal to I will remove a part of it, delete it. P of I to k at n, that is P is nothing but total number of packets that are forwarded by the ith map, that is forwarded by the ith map to its kth downstream node as a mirror router. That is the one of the goals that it had. Where did I write? Yeah, forward the data to the lower maps. That is in the ith downlink. Oh no, the ith map and the kth downlink at n time. What is the data it forwards to the lower maps? That is through this. If k is equal to 1, then what is the data that it forwards to the lower maps in this link? Plus w is some weight factor reflecting the difference in the two computational loads, and q is the computation and managing the mobile nodes registered under that map. So it's the data transferred by this ith map on its kth downstream to the mobile nodes. In this kth downstream, if there are few mobile nodes registered through this kth downstream, then the data transferred in that kth link to the mobile nodes. This is for the mobile nodes, and this is just the data transfer to the lower maps, divided by C is the C computation that is done by the ith map in the for the kth downstream at every time delta t. That's the difference between the time. It's like if n comma n plus 1, then delta is nothing but 1. So nth time and n plus 1th time. So that's the delta. So this is the actual load which is calculated, and now you know what are the terms used in calculating the actual load. And expected load is nothing but the exponential moving average. It's the similar equation. It's just expected load for the ith map to the kth downstream at time n is nothing but some factor r into the actual load at n plus 1 minus r into expected load that was calculated earlier at n minus 1. So this is nothing but the uh, exponential moving average equation that you can see in wiki, or that was there in, that is there in the maths M4, the fourth sem with you students. Okay, these are the equations that I wanted to tell. I think yeah, if the load is sent through the RES field, it's sent as a percentage load. So if it's 100%, it's full. So it's nothing but MIK into 100. So it's the, that gives the percentage of load that is there in the ith map to its kth downstream. So the load decreased tendency and load increased tendency is nothing but the comparison of values between the actual load and the expected load. So load decrease and load increased tendency is decided by this factor. It's the expected load in the ith map at the kth downlink at n. If it is less than actual load at n, then it's the expected is less than the actual load. So actual load is more, so it's load increased tendency. And the opposite is, if expected load was, we expected more and the actual load is less, then it is load decreased tendency. So this is given in the RES field. So this comparison is done, and based on this comparison the first bit is filled and the rest is filled by just multiplying this into 100. That's the percentage load is in the next 6 bits. And what do I want to tell? Yeah, I think everything is clear. And if you want the RES real value is nothing but the max of 0, or m of I to k at n minus 36, that is 6 bits. This is the 64 values that you get, that can be placed in 6 bits. 2 power 6 is 64 values. Finally, I want to wrap up by just telling that the higher maps with load decreased tendencies are preferably selected. If many maps have load decreased tendency, then the map that is higher in the hierarchy will be selected. So higher in the hierarchy, and higher maps with load decreased tendency will be selected. So if there are many maps with load decreased tendency, the one in the higher level of hierarchy will be selected. So I think most of the concepts are completed or covered in this video and the previous videos.